professor at NIST and JQI in Maryland. Michael is one of the most creative theorists I know. He's worked across several different areas of quantum information, error correction, complexity theory, quantum simulation. He was a postdoc. He started with his PhD at Harvard, working with Misha Lukin. He was then a postdoc at Princeton, where I interacted with him quite a bit. During that time, he did some very nice work with Jason Fedor on spin qubits, but also wrote the most early influential papers on the measurement induced and phase transition with David Hughes, and then the team so yeah, very excited to hear about his recent work.
Thank you. Thanks for the very kind introduction. Thanks for having me. Pleasure to be in Stanford. Bay Area native. Back is always nice. Yeah, so what I'm going to tell you about today is what these sort of are calling fault-tolerant compiling and classically hard IP feature. Just the general idea is that this is a problem where we have a particular task or application we have in mind of a quantum computer. In this case, we're going to be studying something called sampling, but we want to do it in a noise robust way. And that's what this idea of fault tolerance. So I'll go through all these terms. So I just want to start off first by thanking Gullans and Dominique for helping with the slides for this talk. And then also I want to start off by thanking my collaborators. So this is going to be mostly presenting two works. So one is a theory project that was involving this postdoc in Maryland, Dominique Engleiter, graduate student at Harvard, Marcin Kalmowski, and Philip Lofstein, who's another experimental, and Alex Kubica, who's at Amazon, kind of helped with the error correction aspects of the work, and then Misha Lukin. And then, of course, there's also this experimental work that was published recently, which I'll present some results from that paper. I think I saw that Dola actually presented the talk on this work, so I'll sort of review what's going into that, but I won't present everything in this paper. There's a lot going on, and obviously a lot of the excellent. Okay, so just the idea that we're sort of pursuing here is just trying to advance quantum information processing. So in the last few decades, we've seen a lot of work on really excellent work on small scale quantum computation with physical qubits. So either atoms, ions, defects, or superconducting systems. And roughly speaking, the kind of goal of this work has been taking these small scale systems and then putting them together and seeing what comes out of these kinds of controllable systems. And so one really exciting direction in that research has been quantum many-body dynamics. So when you have these controllable quantum systems and undergoing evolution, unitary evolution, you have effects like many-body localization. It's from a multiple atom experiment. And more on the digital quantum computing side, you have this beautiful experiment by Google on random circuit sampling where they're claiming quantum supremacy result. So this is more like an analog quantum system, and this is more digital. The focus of this talk will be on more like digital systems. And the other exciting development in quantum information has been what we call the error correction frontier. And so here, what we're starting to see is not just physical qubits, but people putting physical qubits together to make coded or logical qubits. And there's been work on 1 and 2 logical qubits, also gauge that system. This is work that's often pioneered by industry. So this is the experiment from Google, recent experiments, and also Quantinium, which is an ion trap. Okay, but one of the things we've learned from these controlling physical qubits is that it was predicted in the 90s, and it remains true in practice that decoherence is really the central challenge to large-scale quantum computation. And quantum error correction is really the only route to fighting decoherence. And so if you want to go from current error rates to the -3 down to practical error rates needed for useful algorithms in the -10, you really need some kind of mechanism to fight noise. Then a lesson from these early efforts. Okay, so right, so that's where the talk is really about pushing this error correction frontier. And so we need a way to scalably fight noise. So the solution in classical information theory is to redundantly encode information. So if you just copy information repeatedly, then you can protect things. In quantum systems, we have the no cloning theorem. So you can't copy quantum states, and that makes error correction more difficult in quantum systems. But it turns out there's a route around that using entanglement, in particular something called stabilizer codes. So here you encode quantum information at non-local degrees of freedom using entanglement. So you define a non-local subspace by states which are eigenstates of many different operators, and stabilizer codes, and that gives you a way of protecting quantum information. So then the idea of quantum error correction fault tolerance is you have noisy computation, and then during the computation you then detect error events using measurements and decoding, and then you do apply some error correction. And of course, there's this famous result, the threshold theorem, which says that if your noise rate is below some constant value, then you can exponentially suppress. That's the basic idea. So just to give you some example to think about, which has been, of course, very influential in the community. So this is one of the simplest sort of scalable error correction code, which is the report code. So here it's defined on a two-dimensional lattice. Each of these circles is a qubit, and then the stabilizer operators, the poly operators that define the subspace are these E checks and X checks, and then we have the periodic boundary conditions. Okay, so if you work out this code, you'll notice that there's some poly operators which aren't specified by these operators, and these are the logical operators. So there's a sort of X logical that wraps around the torus in this direction, and then there's an including partner, the D logical. Technically, this code has two logical qubits, but that's not so important in this discussion. Okay, so now what's going on when we have noise in the system? So imagine you have some kind of X error on this particular qubit. So what it does is that will flip two of these E checks. So you end up with, instead of being in a +1 eigenstate, you're in a -1 eigenstate. And that lets you infer that there's likely an error on the site class. And the key idea is that as the code distance, so the sort of minimum weight of this logical operator, as the lattice size increases, you'll have more and more errors, but you also have more checks that can kind of fight the errors. You end up with this threshold behavior. So the logical error probability scales exponentially below the threshold. And famous result in the surface code or the core code that the threshold is a reasonable value. Okay, so as I mentioned earlier, so the estimates for large scale, for running interesting algorithms in large scale quantum computers, you need millions of physical qubits. You need logical error rates at this 10 to the minus levels. This is far future from this. And one of the challenges in this topic is just this basic efficient classical control problem. So if you look at a conventional semiconductor computer, there's very clever solutions to the control problem. So using just a small number of wires, you can control billions of transistors. So that's been an important part of the scaling of computers. in quantum computers, the current model has been to, and just by necessity, you actually have to have several control wires per qubit. So that makes this the scaling generally challenging. So that's, one challenge in this setting is this sort of wire problem, which poses a challenge for large scale control of quantum systems. And then the other challenge is that once you're doing fault-tolerant quantum computing or error correction, the logical qubit is delocalized, which is great, but it becomes very hard to operate on or process quantum information. And so, so in some ways, what the results I'll talk about today, experimental results really present impressive progress on this first challenge, and the sort of theoretical results have partially been about understanding, how we can do interesting or hard computations in this setting with delocalized. Okay, so but because of these two challenges, as I mentioned at the beginning, most of the experiments on logical qubits have really focused on one or two logical qubit systems and just a few logical gates. Okay, so then I just want to say a few more words about this idea, fault-tolerant compiling. So if we look at this sort of full stack quantum computer, one way we think about the compiling problem is you have many different layers of the quantum system. So there's a physical control, then there's sort of virtual control, which would be like full shape engineering, things like that. You have quantum error correction, logical circuits, and then ultimately some kind of quantum algorithm. And so what we're mostly focused on in this talk is this kind of step here, going from the sort of thinking about how to compile logical circuits. So from physical circuits to a logical circuit. And the traditional approach to compiling in the community has been mostly something that relies on this idea of optimizing the T count. So we know that for a lot of codes, there's this set of gates called Clifford gates, which are relatively easy to implement. So these would be CNOTs. And then this is a phase gate and a Hadamard gate. And then there's this hard gate, often this way it's phrased, which is the T gate. And the compiling problem is really just presented as a mathematical problem of, given a physical circuit, how do we find the lowest depth and smallest number of gates? That's sort of the traditional view. And that's certainly a valid approach. But in the sort of foreseeable future, it seems like that approach will become, very, very much limits you in what you can actually achieve with current systems. And so the idea is that in the foreseeable future, fault tolerance really needs more of a co-design approach with both the one American code you choose, possibly multiple codes involved, and also the hardware you're working with, and even the application you have in mind. So unfortunately, you have to look, across the full stack if you really want to push towards. So I think one of the really exciting things is something that I definitely learned from this collaboration. My background in the last few years has been mostly in solid state systems, but these AMO systems offer really enormous flexibility to explore this on intermediate scales. In particular, two important points are they often have extremely long coherence times. So the qubits can sit around for a while without decohering, and that gives you flexibility in the compilation. And also you have sort of a lot of methods for long range connectivity. So you can move qubits around, you can use cavities, many different approaches to achieve long range connectivity, and that has a lot of advantages for fault tolerance. And I think that the broader vision is that these kinds of efforts inform scalability really on all platforms, even though we're exploring this. So with that, that's sort of my introduction. So now I'm going to introduce the first hero of the talk, which is these reconfigurable atom arrays, which are based on neutral atoms like rubidium or alkaline or alkaline earth atoms, rubidium, strontium, ytterbium, uranium. Atoms of this type, one or two electrons in the outer shell, and they're each trapped in an optical tweezer, and that's great because then you have you can potentially have millions of atoms evolving in the system, and you can control them with optical beams, so you can do single qubit gates in a very simple way. The sort of challenge in the system, of course, is implementing the 2-qubit gate, and that's where there's been progress in the last decade or so using Rydberg interactions. So you excite these atoms to very high lying Rydberg states, and that lets you turn on and off long range interactions. And so you can implement, for example, a controlled Z gate just by bringing two atoms together and then exciting them to the Rydberg state. So yeah, so two important points about this architecture is you have this non-local connectivity. So you can actually, because they're optical tweezers, they can be moved around with standard optical, like now standard optical tools. And you also have this ability to, again, because it's optics based, you have this ability to do very efficient parallel control. So just a few wires can address many qubits. And so just to see how that works, this is an example where using these kind of optical tools, they're implementing parallel single qubit gates on every other, this is experimental result, on every other atom in the array. So you have this array of rubidium atoms, and you're just undergoing Rabi oscillation, sort of control of Rabi oscillation. So then the other point is this parallel entangling gate, and this has been really exciting development. So here, imagine you have two-dimensional arrays of atoms, block 1 and block 2. You could even think these are two surface code sort of blocks. Now you want to do an entangling gate. So what you can do is just literally move all of those atoms next to the other ones, apply a global control field. So there's no local control in the system, just a global drive, and then you entangle every atom in the block. Then you separate them.
Is interblock entanglement into that, or?
Yeah, that leads to entanglement, say, between this qubit and its partner on the other block. Right. So these are early experimental results from the looping group, and also towards collaboration between Harvard and MIT. So here they're showing very high fidelity CZ gates, or at least relatively high fidelity of 99.5%. But what's most impressive about this result is that it wasn't done just with one qubit, which is what I'm familiar with in solid state systems. We would optimize entanglement gates on one qubit. In this setting, this was done on 50 qubits simultaneously. So that's really really pushing things quite far when you can do something. Okay, and then another ingredient they have in the system is the ability to do the measurements also forward. So using FPGA. This is definitely a limitation. So there's two limitations I'd say in this architecture I'm presenting. So one is motion is slow, and then also in these neutral atom systems, readout is slow. But there's still interesting things you can do, of course. Okay, so now let me just present a kind of vision for the logical quantum processor in this sort of non-local architecture. So we want to do when we want to do what are called transversal gates, so single qubit transversal gates. So that's a gate that you achieve just by operating on each qubit in the code block. So imagine these are each some small code, possibly the surface code or some other code, and then you apply sort of single qubit gates on every qubit in this block. You achieve a logical operation, parallel and efficient way. And then when you want to do entanglement gates, you do this motion type. So in a lot of American codes, there's an entangling CNOT gate that you just get by doing a transversals. So that can be achieved. And the sort of way that this is laid out in their system, they organize this by thinking about a zoned architecture. So you have logical qubits with like a storage zone where you do these single qubit gates. Then you have and you also have some reservoir of qubits. Then you have an entangling zone where you do these 2 qubit gates. And then you also have this readout zone where you can extract syndromes or enter the system during the circuit. Okay, so any questions about the architecture? Okay, so now I'm gonna so the last part of the remaining part of the talk, I'm gonna discuss these sort of IQP circuits. In particular, hypercubes are going to make a really central appearance. Okay, so the question we started with here was, can we do computationally complex transversal quantum computation? So we saw in this architecture that it was very easy to do transversal gates in the system. There's still a challenge in quantum correction that comes to a very fundamental result known as the Mill theorem, that if you only have transversal gates, there's no universal gate set for stabilizer codes. For actually any distance greater than 2 code, there's no universal gate set. So you might worry that limits you to sort of boring computation. So possibly you might, in some cases, you're just limited to Clifford circuits, which are your classical simulator. Okay, but that turns out not to be the case in some situations. So when you only do these, if you restrict yourself to these type of transversal quantum operations, you end up with a sub-universal model of quantum computation. But in some cases, you can do something called IQP circuits. So IQP stands for instantaneous quantum polynomial, and I'll explain it by giving you the code where it's sort of achieved, or family of codes where it's achieved. So there's this nice family of codes called they're d-dimensional color codes. So you have 2. So d is the dimension. So imagine this is now a hypercube in capital D dimensions. So there's 2 to the d qubits. It has d logical qubits. So in 3 dimensions up to 3, and then it's a distance 2 code for every d. And it's something called a CSS code, called a Shor-Stein code, and that gives you the ability to prepare states and also measure them in the x and z basis. So that's actually nice because you can sort of just using transversal operations, you can measure in both x. And then the other feature of these codes is they have diagonal non-Clifford gates. So they have gates that are sort of, have the potential to be hard to simulate. And so what an IQT circuit is that you prepare in the x basis, you apply these actually just diagonals. So these are gates which are diagonal on the z basis. You apply diagonal gates and then measure in the x basis. And that's so that can be achieved in a sort of efficient way in this model. To get universality, you need, again, some extra ingredients. So before I said I gave an example, the T gate. In this case, it's the Hadamard gate, which is needed to use universality. And so you get that with something called, with using magic states for Hadamard. Okay, so the sort of smallest interesting example of this color codes, at least in the context I'm talking about, is actually the 3-dimensional version. So the 2D version only has Clifford gates in its set, but in 3 dimensions you actually get something called a CCZ gate. So you have 3 logical qubits, and you can implement a CCZ gate, so control Z gate, by acting with, by just doing physical single qubit rotations. The other gates you get are the CZ gate. There's also a class of, they're not transversal gates, but they're called permutation gates. So you can implement CNOT gates in the block using permutation, just relabeling qubits. And then you of course have this transversal CNOT, which lets you entangle blocks together. And if you're interested in the code itself, so as I said, it's defined on a three-dimensional hypercube. These are the X logical operators, so they're sort of the faces of the cube, and the Z logicals are this line. You can see why it's distance 2 because it's V. And so there's 3 logicals associated with the 3 sort of faces. Okay, so this is sort of arguably the second hero of the talk, which is these interesting color codes. And so one basic result we noticed early on is that the actual gates that we have is, as you saw, it's Z gate, well, poly Z gates, which aren't so interesting. You can do CZ gates, these are Clifford entangling gates, and then this CCZ gate, which is a non-Clifford gate, and then the CNOT. And it's actually a very simple calculation to see that if you take any I2P circuit, or if you take any circuit defined with this gate set, it's actually just equivalent to a different circuit with only diagonal gates, but on a different graph. So the CNOT gate doesn't add extra power to the computation. It just gives you a different connectivity. So we're sort of, because of this, we're sort of confined to this I2P. But we do have enough control that with this D-dimensional color code, we can perform arbitrary degree D IQPs, where D is degree D means like the number of qubits involved in the. And this was shown in 2016 that actually, if you sample a random degree 3 circuit, so that's D gate, then sampling from that, run a random degree 3 circuit and then sample in the X cases, that's classically intractable.
Well, that's very important.
Yeah, it's so it's what you get by starting in the X state, applying diagonal gates, single Ising gates. So it's basically an Ising, Ising evolution, and then you measure in the X state. So what the Ising interaction does is it puts. So you're creating a superpositional computational basis state, and they get phases. And then when you measure in the X basis, the measurement probability is actually sort of like it ends up being a sum of all these phases together. So it has both pluses and minus signs. Right. Roughly speaking, minus hard, sampling is hard.
And ITP is integral. What is it stand for?
So the reason I haven't been writing it out is because I don't think it's important.
Okay.
It stands for instantaneous quantum polynomial. So it's instantaneous because you can do it with the diagonal circuit, which means you can do it in depth 1. It's quantum, and then polynomial just means it can be implemented with polynomial. Right. So sampling from this, so just to come back here. So sampling from these circuits is hard. That was shown in this nice paper, which kind of helps inspire this later work by the Google group on hard random circuits. And then it's another interesting feature of running random circuits is that they're useful for benchmarking. So if you want to say something about how good your sort of whole stack quantum computer is, running random circuits tells you how, gives you a measure of quality of this. So the other important ingredient, and this is where another hypercube comes in, is that we sort of came up with a very efficient ensemble that can be implemented on this sort of this reconfigurable architecture, and that's a hypercube of logical qubits. This is not the hypercube is now the interaction graph for the IQP circuit, and so this is what it looks like. So for d equals 1, it's 2 blocks, just a line. D equals 2 is a square. 3 is the cube, and each of these lines is like imagine a CNOT gate that's coupling these logical blocks, and then d equals 4. You start getting into things which you can't draw very well, but this would be a 4-dimensional picture. So one thing you can notice about these graphs is that they're something called expanding graphs, so they're very everything is very close together, but they're also sparse. So if you run, so we're going to be running circuits on this kind of architecture. And so what we do is we apply, so in each block, we can do random degrees, 3-qubit IQP, random IQP. We do random CNOTs on the hypercube edges. And then we can also do sort of permutation gates, so in blocks. I'll come back to why this is important. Right, so this is the sort of problem we're studying. So this is hypercube IQP circuit sampling. And so so remember we have these, this is the 832 code, so we have these 3 logical qubits. So this is the IQP part, these are the permutation gates, and then these are the transversal CNOTs. And this is constructing a depth 2 or a hypercube, so square, and we're doing what we call hyper depth 1. So you could then repeat this multiple times to get higher quote. So the sampling task is you prepare this logical plus state, and then you apply these kind of random operations, and then you measure on the X basis. Something we've added recently again is these in-block permutation gates. And the experimental results, which I'll also present, so far they were done without the permutation gates and all. Okay, so this is what this is one of these famous, or at least my recent time famous movies. So this is showing what the hypercube circuit looks like for the actual atoms moving around. So these are all these rubidium atoms, and each time they get, so we're doing, when they get picked up, we're doing one of these transversal entangling operations. So in that step, we constructed half of the hypercube, and now we're constructing the other half. And then eventually they're all gonna come together. So that's hyperdepth 1 for the 4-dimensional hypercube. And you can see that it involves a lot of motion, but it was all sort of maximally efficient in a sense, because during every operation, all the qubits were. Okay. So now let me say something about some more practical results about complexity and benchmarking with random circuits. So in this problem of sampling, what we're studying is this output distribution. So you start in the sort of fiducial state, which in our case is the X states, apply a circuit, and then sample in the same cases. And this is distribution. One of the ways we characterize sort of the hardness of these circuits by looking at something called scrambling and also something called anti-concentration. So it turns out you can measure both of these properties by looking at the average collision probability of this output. The average collision probability is the sum of the square of this distribution, so sort of like the average probability of each bit string. And then you can also average over the circuit. So if you have an exponentially small collision probability, so if your likelihood of seeing the same sample twice is exponentially small, that's some kind of indication that you have both scrambling, so quantum information is highly delocalizing the system, and also hardness. So the sampling test. So the other type of quantity we're interested in is the average fidelity. So it may not look so closely related to the collision probability, but it turns out that in some ways these are very similar observables. They both involve two copies of the quantum state, or sort of. So this is the average fidelity is you compare a noisy implementation of the circuit to a noiseless implementation. The problem with fidelity is that if you only have one copy of the state, it usually requires exponentially many samples to measure. Benchmarking circuits based on fidelity is generally pretty challenging. So that's where this quantity, which sort of connects collision probability, fidelity comes in. It's called the cross entropy benchmark, which was introduced by the Google group. So here, instead of taking, this is two copies of the noiseless circuit, you take the noiseless circuit and compare it against the noisy circuit out there. And then you're looking at the sort of rescale collision. So the problem with this method is it's computationally inefficient. It requires you to compute. So you can get samples a simple way just by running the one computer, but to get to actually compute XCD, you need to also compute this probability, which is generally exponential. But one of the arguments, so that's okay in some sense because the sampling. So what we really care about is the sampling task, and it's a verification of the samples takes exponential time. We can sort of live with that. And one of the arguments for why XCD is a helpful quantity to look at is that it actually approximates, or it lets you estimate the fidelity. So there's a really close connection that was argued between XCD and fidelity. And in some cases, that's definitely true. But it was also noticed in this work by Gao and our collaborator Marchin and others that there are regimes where this isn't the case, right? So where XCD and fidelity actually deviate from each other. In some of our recent work, we sort of sharpened this notion to show that there's a phase transition between these two regimes. So in one regime, sort of at low, so there's phase transition with the noise rate. So at low noise rates, the XCD and the fidelity do approximate each other, but then there's a sharp phase transition where at higher noise rates, the two deviate. And what this means is that XCD is a reasonable way to benchmark fidelity, but you really have to be careful. And also, you can see this is really motivating the use of error correction for this kind of problem. Because to enter what we call the sort of healthy regime, you need error rates that scales 1 over. You need error rates to go to 0 as you scale up. That was definitely a central message. Okay, so that's, and then this was all done for what are called par random circuits, where the gates are 2 qubit gates are drawn from just our random ensemble. I'll come back to this in the IPP case where we find similar studies. Okay, so now let me say a little bit about the sort of properties of these hypercube IPP circuits, and here we're adding these permutation gates. So one thing you notice is that, so you take a fixed system size and then increase what we call the hyperdepth, which is just this, basically the depths of the circuit within that architecture. Then already at hyperdepth 2, which is a log depth circuit, you get properties. This is the distance of the graphs you get in the IPP ensemble to the random IPP circuit. So they're already at hyperdepth 2, so very low depth. They're very close to random. And you can also look at the collision probability, the ideal XCD. And then again, at hyperdepth 2, everything sort of collapses to sort of random length p-value, which in this case is 2. And these were done with Clifford simulations.
And random IQB is the hardest or.
Yeah, that's sort of the
Okay.
ensemble we want to achieve. Sort of what we're trying to. Okay, so this is showing that by these measures of scrambling, hyperdepth 2 and beyond is, I mean, actually even hyperdepth 1 is sufficient for hardness, but there seems to be like a really sharp distinction between hyperdepth 1 and 2, which is interesting to understand better.
Are these using the CCZs or just the CNOTs?
So in these simulations, we just do CZ gates and we do Clifford.
Just Clifford gates, yeah.
It turns out that for these kind of observable, well, not necessarily this one we do into the CCC gates because this is just computing graph properties. This one, for this, we're doing actually the CCZ gates don't change the XUD. So for technical reasons, this is sufficient. Good question. Okay, so the other thing we looked at is this correspondence between XED and fidelity in these circuits. And one thing we generally see like that for the kind of regime we're interested in, we're in the kind of healthy regime of these circuits. And then when we look at the approximation of the fidelity by the XED, we see that we at least so far we're not seeing evidence of the state transition. So this is a sign again that we're in this kind of. These are these simulations on 48. Okay, so now let me say a little bit about the classical hardness of simulating these circuits. So one kind of class of algorithms you think about are just tensor contraction. And so we can guard against, by looking at these effective graphs that we get, we can study something called their tree width, which is kind of a lower bound on the tensor contraction. And we see that, at least by this measure, again, at hyperdepth 2, the tensor networks that come out of these circuits tend to be likely very hard to contract. So there's another class of algorithms which are specific to this setting we're in, so this wouldn't apply in our random circuits. These are called something called Clifford plus T simulators. So here if you have a quantum circuit with a small amount of like qubits that are needed, or a small amount of magic that's needed to implement it, then you have another class of classical algorithms that can attack it. And this particular algorithm was discovered recently pointed out recently by this group from IBM and IMQ. So they were studying the circuits we implemented, and they noticed that they have the special structure which lets you go from a 2 to the n algorithm to a 2 to the n over 3 algorithm for simulating, which it's still exponentially hard, but in setting you're often fighting for every qubit. And so, but what it turns out is that by adding these permutation gates, you can avoid this attack. So this y-axis is the log cost of the algorithm they developed. It turns out you can find the attacks that they implemented by solving something called a graph problem called linear vertex covers. It's NP hard, but it's easy to solve on these. But anyways, I mean the message is that by modifying the circuit family, we're able to sort of avoid this kind of near Clifford simulation. And as far as we can tell, this has been studied somewhat systematically. these are really the main two attacks people have for IQP circuits, either internetworks or. Yeah, so any questions about?
So what's your intuition why the XCD breakdowns at a certain value is actually times 10?
Yeah, it has to do with, well, we have an interpretation using like sampling from random symbols to statistical mechanics problems. I think one intuition Martin likes to give is that, so in when you're doing sampling, you can like add a bunch of noise at the final layer of gates, which doesn't affect the outputs, right? You can basically apply any Z operator or an RTSX operator. It doesn't affect the sampling quality, but that would kill fidelity. So there is a sense in which, you know, the samples have, like in certain noise models, the two have to respond immediately. And I guess what the space transition is when you have more like a standard local noise model and you're looking at evolution. But yeah, I can say a lot more. It is.
Yeah, have you put the thought into like average case attack algorithms on these sorts of circuits? Because you know, you're defining some particular random ensemble of circuits, and you know these tensor contracted plus these simulation algorithms actually work for any circuit. Or you know, and one generally might worry that you know random instances could be easier than worst case instances. This is actually something that seems to be a little different about your circuits from RCS, from random circuit sampling. It's like this flavor of IQP. We don't know how to prove average case hardness. Sorry, yeah, is this something you thought about?
Yeah, I mean, I guess the technical point is that in the reduction proof, you use the continuity of the gate set.
Exactly. Yeah. All of our arguments for hardness of average case circuit will require your continuous gate set. And here you're really, because of the transversal thing, you're always going to be fundamentally restricted to discrete.
Yeah, so I mean the intuition is that that's not crucial for the average case hardness.
Yeah.
But I would say it's maybe more a challenge for you.
Sure. Yeah.
To improve your proof methods.
Yeah.
But yeah.
No, it's a nice question.
I tried to convince Bill. Yeah, I'm interested in it as well. There is some reduction.
Yeah, there are things in variants of IQP continuously, but this is a slightly different thing.
Well, I mean, even for discrete, there's at least one reduction.
Okay.
But it doesn't apply to ours.
Sure. Yeah.
5 minutes.
Yeah, perfect. Okay, so one of the technical sort of developments we had in this work is we developed a new statistical mechanics mapping for IQP circuits. And this is really what it's doing is we have a lot of work now on these R-random circuits, and we basically adapted all of those methods to IQP, which is kind of missing from the study of IQP circuits. So there's a nice story about statistical mechanics mapping for IQP. Basic intuition is that our random circuits, you sort of study them for the second moment quantities by thinking of them as spin and half models. So you have a way of mapping the degrees of freedom to spin a half. IQP, you don't quite get, there's more structure, and you don't end up with just 2 degrees of freedom, you end up with 4. We have to study a stat-mech model with 4 spaces, right? But what you win is the rules are actually much simpler, at least for the some family of circuits. So it's kind of what we call a survive or die model. So things either live or they get killed. It's simple. Then noise. This is a bit too fast. With the experts, I think this is an interesting aspect of studying these things. So with this fatback mapping, we can prove some new theorems about IPP circuits. So one is we can prove we have improved proofs of anti-concentration for sparse and sparse IPP. We also have some analytic understanding of this hypercube IPP model based on this fatback mapping. And another nice result is we can prove the existence of these two regimes at different noise weights. There's one regime where XCD approximates fidelity, and then the regime is. We now have, at least in this model, a rigor. So now let me go quickly through the experimental results. So this is the circuits we're running. So we're gonna, again, we're gonna come back to error correction or error detection. So at the end of the circuit, we're gonna measure some stabilizers, and that's gonna give us like some confidence in each sample. And what this shows is from simulation, this is the XED score we get versus like the acceptance of those samples. And this line is a bit to certain power law, which you can derive just by thinking about the research. These are the experimental results. So here, as you go from no post-selection to complete post-selection, you see even at the level of individual circuits and individual probability distributions, you see an increase of overlap between the two distributions. This is something you can study on small systems through a lot of sampling. As we scale up, we use this XCD as our benchmark, and then you can see that adding error detection lets you improve your XCD score by the factor of 10. So now let me spend a few minutes talking about the scaling to larger system sizes and also scaling to larger or more complex circuits. So one thing as I mentioned at the beginning, you don't just have the three-dimensional version, you can go to higher dimensional color codes. And then instead of just CCV gates, you get this to be a degree 4 gate. This is on a 4-dimensional hypercube. And with Alex Kuka, we constructed infinite families of color codes with this property. We have using single qubit gates, you can implement these IPP circuits. And that leads to a type of threshold theorem. So if you can combine our code families with some results from Gottesman on LDPC codes, then it implies that there's there's a low enough noise rates will have exponential suppression of errors. Okay, so the other interesting direction that we explored is it's not to computational based sampling, but it's called Bell sampling. You measure in the Bell basis. Let's do things like measure entanglement or purity of subsystems. So here, this is approaching something called a page curve, and you can see that error detection is helping you sort of improve the quality of your measurement. So you can think of this as moving more in the lines of quantum simulation, where you're studying sort of quantum chaos. So another application of Bell sampling is that we, in a work with Dominique, we showed that it gives you a way to avoid this exponential cost of verification, at least under some assumptions. And then for IPP circuits, it turns out that those results go through if you have degree 4. So if you have this 4-dimensional color codes, then you can get hardness of this. So we have potential for also not just scalable, but also efficiently validated quantum advantage. And let me just now end the talk with some outlook. Yeah, so I think one of the main messages of this work, at least in the near term, is that we're sort of presenting a practical path to classically hard sampling with logical qubits, and so I'm optimistic that that will be able to run such circuits to see what we find. There's another message about fault-tolerant compilation, which is this co-design of the, generalizing beyond just sampling, really have this co-design of the code and the hardware. Sort of improve towards faster applications. And other things you could think about in this setting would be like quantum simulation, maybe proofs of quantumness, or this bringing on. Another exciting direction on the hardware side is that this reconfigurable architectures are really pointing to a sort of shortcut to low overhead tolerance. And this is an outlook from more from the experimentalists, but they're arguing that you could start to see systems with 100 logical qubits and gate arrays at this minus 5 level, which is really a big change in how we would think about near-term algorithms. And then the last few seconds, I want to advertise if you're interested in these topics. We got this exciting news just this week that we're going to have a KITP program next year, which is maybe more general than just fault tolerance, but really looking at noise robust phase matter. And all our my friends are helping, so I hope that you can join us. Thanks.
It. Start with the student question.
Guess I was wondering, I know these results on hypercubes, but are there like generic other families of graphs that you would be interested in looking?
Yeah, so where we started was just random graph. That's where your mind would go and think of local activity. It turns out, and I didn't go into this, but for the Rydberg system, you're actually pretty limited in the types of graphs you can efficiently parallelize, because you can pick up arbitrary you can pick up subsets and then you can move them around, but you can't draw. You can have like crossings in this way, and so there's ways around this, but that does generally limit what you can do. And what this hypercube is something where it doesn't involve any crossings, and so that's why we focus on hypercube. But I think there's many other graphs you can consider, probably also with that similar property. Another thing we're thinking about is that once you have the hypercube, you can then go embed any other graph you want in it. That would be one route to getting like more general circuits. We need to do. And then I could also say in this graph systems like Quantinium has developed, where it's also based on shuttling ions around. The constraints are different, and there you can do much more general. Like there, the random graphs are actually practical. These are interesting.
In what sense are IQP circuits like not universal?
Yeah, so they're not universal without adaptive measurements at the end. So if you can make a measurement and then do something different based on the outcome, then you get universality. If you just want to implement, if you just do this non-adaptive measurement, what it is universal for is with post-selection, sort of for the reason I just stated. So if you can post-select on the outcome, then you get universality. And the hardness of sampling, sort of as Adam explained, also goes through the universality of post-selecting.
So actually, I have a question about this, future sampling experiments with logical qubit you had first sentence.
Right.
So if I was correctly, so in the previous slide, you were using some easy circuit for this IQP circuit, to basically benchmark, right, your system. So I was wondering whether there's some equivalent notion of hard circuits on this IQP architecture. And it's the,
When you say easy, you mean,
because in Google's experiment, they basically have like some easy and hard connectivity.
yeah,
Basically, yeah.
right, so this circuit, we had a sort of an inter-network attack on it that included the N/2 algorithm.
Mm.
So we could do 48, with our approach, we be able to really do 96, I guess. But this other N/2 algorithm, it's not depth, it's interesting because it's not depth in them.
Mhm.
So that one go up to 2^3, get up to 3 times 50. Yes.
Yes, more simply speaking, from experimental point of view,
Yeah.
what be the like possible, critical system size and the number of qubits, which becomes like classically intractable when you
Yes.
do this sample experiment with logical qubits.
Right, so what we think is that when you get to like 50 or 60 qubits, basically the best algorithm, if your circuit is deep enough, then the best algorithm tends to be a state vector simulation. And if your fidelity is high enough, your fidelity is like. And then in that regime, we can guard against both internetworks and also these near Clifford simulators because you can sort of guarantee that there won't be a version of this near Clifford simulator by solving this minimal vertex cover problem. But yeah, it's definitely risky. I mean, yeah, I guess you should. It's always about the scaling, right? So you shouldn't get too hung up on the actual.
Yeah.
But
Sure.
But it's a bit bigger for, like, do you agree? I thought Maslov had all said something like, oh, you need 192 is where they're things that really break,
yeah, they were talking about this
the Clifford's less TV attack.
the N/3 algorithm, so that applies to the circuit without these in-block CNOT gates. And it's interesting the reason it works. I mean, it's an interesting general attack on circuits, but it really it's immediately broken when you add these permutation gates. There's a subtlety there because permutation gates and transversal gates, they're both individually fault tolerant, but when you put many of them together, and the errors can start spreading. So you need more error detection in general.
Not just at the end. Yeah.
But it's a question of
I guess one question is like at a very high level, would you always expect that these IQP, like low depth IQP results will kind of require more qubits than something like random circuit sampling, just because they're going through, as part of the proof of hardness, going through something like measurement based on computing and post selection, which then always involves more qubit overhead?
I mean,
That's what you'd always expect.
I mean, my intuition from studying IQP is that there's not much important difference. I mean, computing in IQP is solving. I mean, it's basically solving these spin glass models and very complicated geometries, which is much easier than circuit. But if somebody finds some like general attack on IQP, I guess also spin glasses and sometimes it doesn't work for algorithm circuits and how
Yeah, that's
massive.
Yeah.
But it's unlikely based on.
Okay, so you don't think it's like fundamentally easier? It's like fundamentally requiring more to like, okay, maybe just a factor for you.
Yeah, I agree. So what's known rigorously is that the exponent is it's less than 0.2, it's 2 to the 0.96. There's a 0.96.
Oh, interesting.
It's not exactly.
It's a little less than 2 to them. That's good.
Oh, yeah, so obviously, like, the point of this is that it works for logical arguments. But I was just kind of curious, at this particular stage of technological development, like, if you just, let's say, did the same hypercube graph, but just like in the bare circuit physical basis, like would it, like how would it have performed? Because then A, you get your continuity and all that kind of stuff, so you could add, and B, some more qubits. So like would, and you're doing error detection at the end, not during the middle, so you're not, I mean, you know, it's not that different maybe than the mitigation stuff that you might do in the.
Yeah, it is a type of mitigation.
Yeah.
If you had a distance 3 code, then you would get correction.
Yeah.
So. Yeah, so I think one, I mean, this is not something I emphasize, but I think one of the interesting perspectives on this work is that if we try to implement the exact circuits we did with logical qubits, with physical qubits, we think that you do much worse than you can do with error. So that's what this dotted line is, this blue line. The reason for that is the CCZ gate. So that if you try to decompose that into physical gates,
Sure.
that's a complex operation. So yeah, so with this logical qubit algorithm, we're able to beat, we sort of we're beating physical qubits for this specific task. If you define the task more broadly as one should, is like sampling our circuits, then yeah, it's not as clear. We haven't really studied that much. But I suspect that in this Rydberg platform, you can do extremely good supremacy experiments without qubit quantum.
Also CCC are contribute to the log diagonal Z.
So yeah, so that's one of those things where, like, that's what goes into this. But that's one of the things that you could try to put in the upper bound. And just in general, multi-qubit gates are not easy to. Nobody really knows why, but
Where it's encoded, they're actually easy.
yeah, right.
Yeah.
Yeah, I mean, yeah,
Yeah, I mean, it obviously, like, your point was a different thing, that's the important thing, but I was just kind of curious if you had thought about the.
I mean, I think it's good to, it's definitely good to start thinking about fault tolerance because we have to get there eventually. So, but yeah, I think if, and my understanding is that, like, Quantinium also has this non-local architecture. I think they're thinking about physical circuits because they don't really have enough qubits to do. It's a great question. I don't have a question.
Okay.